I mean, we've heard a lot of excellent talks that went into the details of what we've learned over the past 10 years and what we hope we can learn in the future. But I would like to bring it back to the bigger picture for the audience, because many of the people in the audience are not the expert on particle acceleration. What I would like to discuss is a little bit to talk about the things that we can really say with reasonable certainty about particle acceleration in the universe. So I open the floor either to people in the audience or here on the table to make a short statement about what you think we know about particle acceleration in the universe. Yes, please. Thank you for taking this.
Here's a microphone.
I think we definitely know that the most important acceleration is the first order Fermi acceleration. And this acceleration can be produced either by shocks or by a connection. We're really groping for basic facts for both processes. And as we, at least it's my experience, understand better turbulent processes, which cannot be ignored in either process, we find more and more puzzles, more and more interesting events to study.
Yes, John.
I have an immediate question for Alex, which is going to sound.
Wait, can you please wait for the microphone?
I have an immediate question for Alex, which is going to sound rude, but it's not meant to be. I find the stuff that you guys have done is very impressive, but I always lose track of, and I lost track of again today, how many knobs you're turning to get the interesting answers. The one I can remember from today was you invoked at some point density fluctuations upstream from a shock in order to do things. This is fine, that undoubtedly happens, but it provides, particularly in comparing to observations, typically an almost uncontrollable knob that you get to diddle with on trying to say whether anything is real or not.
Yeah.
So
I think I understood your question, and the answer is none. We are not using anything which is not in nature. And as I showed you, that even if we don't have turbulence, we don't need the knob to have turbulent eye connection. We simply earlier on did not have enough resolution to see it, but now we see that we start a connection without turbulence, and it develops turbulence. Not only we, but people doing 3D peak simulations. As for the knob about shock acceleration, unfortunately I did not have time to describe more this work. It's published work, and so we can discuss it in more details. We were using exactly the density fluctuations, which are following from this big power law in the sky that is somehow accepted idea, accepted data, and from this data we were obtaining that we can have a generation of magnetic field which is around 1,000 times more than in terms of energy than from the Bell's instability. So I think if anything, we are underestimating the fluctuations of density in the supernova shocks, because these fluctuations of density around the evolved stars are probably larger than we assume. So
okay, so if I can briefly interrupt. So if I understand correctly, the statement is we know that first order acceleration, shock acceleration is very prevalent, and at least according to this exchange that you just had, I have the feeling that you're saying that we understand it, at least the basic principles.
Well, basic principles, but not the details.
Yes, okay, okay.
But I thought you were referring to
Let's.
both shock and reconnection.
Yes,
okay,
yes.
sorry. Yes, yeah. Okay, let's move to Roger.
Okay. Let me take up your challenge, Stefan. I would answer with the general statement that nature is cleverer than we are, and the range of particle acceleration that we observe throughout the universe is really quite extraordinary. I think there are new mechanisms out there that have not been properly described or considered, and I would also say, thirdly, that we're at SLAC, which is the LA stands for a linear accelerator, and new inspiration for terrestrial particle accelerators could well come from not mimicking but thinking about the processes that one sees in the universe, and jog one's mind to think in other sort of different ways, perhaps in a technological context. So that's a sort of very general statement, but I think that the most important thing is the Fermi and other the gamma ray observations and so on have, and radio observations have, I think, in the solar observations have challenged the contemporary mechanisms for particle accelerations, which undoubtedly operate and are undoubtedly important. There's nothing wrong with them in the generic sense they're there, but they challenge them in such a way that I think we are searching for new mechanisms, and I think that's the exciting prospect for the next 10 years, is that these mechanisms will emerge and will be thought about theoretically, observed perhaps in laboratory experiments. That's one of the great frontiers, is to do laboratory experiments that relate directly to the plasma physics of particle acceleration, and also the major large-scale simulations that can now be performed in single theses that were undreamt of 5 or 10 years ago.
Thank you, Roger. Other comments or questions?
I have a question.
Yes.
I have a question to Angela.
Oh, very good.
So, what produces ultra-high energy cosmic rays?
Not first order Fermi acceleration.
Yes.
How do you know that?
No, I don't. I just thought it's the right approach, right? Okay, well, I just did something. So you saw we don't know, right? So I think that's sort of along the lines of what Roger is saying. I was definitely going to exactly comment that the first order seems to be a wonderful mechanism, and these guys know way too much for their own good, because we are talking about 20 orders of magnitude, and maybe that's the same hammer that's going to nail all the nails, but maybe not. And certainly from what we're seeing at the ultra-high energies, it's not so easy to do it with one nail. So we're definitely seeing things that were not expected. If we didn't measure, we wouldn't know. So I don't know. I don't think it's clear that it's first order Fermi acceleration. Also, I just wanted to, second on what Roger was saying, that I just saw very recently a paper on wake field acceleration around AGN. It's an example of people who are actually working on the lab trying to do actually high energy physics that are now sort of bringing these kinds of ideas to our world too. So it goes both ways. I don't know if it works.
Okay, Roger,
Just
want to
one-
respond, or?
I'll just respond to what Angela said, and she won't be surprised by this. I wouldn't give up on first order Fermi acceleration for the highest energy cosmic rays if they are indeed iron, because although we do not understand the details of how it works at shock fronts, and I'd be the first to admit that, it's just simply scaling from the impressive acceleration that we see around supernova shock fronts to the shocks around clusters, looks like it could do the job.
Can I say that? Yeah, I was just being polemic by saying that not first order. It could be first order. I think the reality is once we start measuring, we see so many bumps and wiggles that, the power law, using power laws to describe half an order of magnitude becomes a little tricky. So, this is where we are right now. We need to measure more to know, where does the power law really is a power law, and what's the effects of propagation and all kinds of bells and whistles that come in. But yes, it could be first order Fermi acceleration. That was more of a joke.
Jim, you wanted to make a comment?
you know, I think the heliosphere observations are suggesting that particle acceleration is surprisingly efficient. You know, there's a paper back in the 70s that Bob Lynn wrote, and they were claiming that, well, the conversion of magnetic energy into energetic particles and flares was very high. The fraction of energy going into the energetic particles was high. And of course, you go back in the 70s and you might have doubted whether he was really right there. But then when RESI went up, RESI spacecraft went up, and then there's a series of papers in 2004, 2005 saying the same thing based on the RESI observations. And then these recent over-the-limb Crocker observations where they actually directly measured this means that, I mean, and this is something which I think it would have been very hard to argue in advance that you're going to believe this, that the fraction of energy going into the energetic component is very high. And then, you know, the recent crossing of the Voyager spacecraft with the termination shock, they actually saw the slowing of the solar wind on the approach to the shock, which seems to be correlated then with the energetic particle produced at the shock feeding back and slowing the solar wind velocity upstream, also suggesting that the energetic particles really do feed back on the shock itself. So these various things, I think, mean that it's surprising how efficient the production of energetic particles is.
And I think this is also something that is supported by gamma ray observations recently, so I think there's a common thing there. Yes.
So I have sort of a practical question. So a lot of these questions that we want to make progress on require new large observatories. And at the same time, the funding agencies are facing squeezed budgets. And one way they're responding to that is, as Neil mentioned, they're sort of narrowing the scope of the science that they want to do and drawing the boundaries between topics and between agencies more firmly. And it seems difficult to get projects funded now that would run across agency and discipline boundaries, as Fermi was. So is there anything we can do in the community about that?
I mean, that's a very good question, of course. It's like the $100 million question. Yeah, Neil, please.
Well, there are useful things you can do with more focused missions, but I think for bigger ones where you're going to really have a huge payoff, it really takes the community pushing for years and years and trying to find the ways that it excites both or all three agencies. And I don't think it's hopeless. In fact, I think it's probably the way, at least for space mission, the only way that we could get something. But on the other hand, you can do useful things with things like GEM-USO, a very small mission. You know, there still are things to be learned from small missions.
Oh, yeah.
Can I just follow up on that? One thing I think that, you know, a lab like this one or other DOE labs can really help, and so does NASA, and NSF less so, is on the R&D part too, because, you know, if you have a big vision, you know, we are living through a difficult time, but we have to think 10 years, 20 years down the line, and the big vision, in my opinion, in the ultra high energy is to go to space. And the big challenge there is seeing things from far away. And we're not the only ones worrying about that, as you probably know. You know, there is a lot of overlap technology with photo detection from other efforts, let's put it that way. And I think we are a little bit behind, actually, in the science world. So, you know, I'm told there are all kinds of UV background studies that I can't get my hands to and things like that. So I think we have interesting things that can keep a young, you know, effort going, in the main challenge being seeing things from far away, being able to reproduce these, in my case, ultra high energy cosmic rays, extreme energy cosmic rays with better technology. So, you know, you don't need to have everything in place, but you need to have some sort of marching, you know, direction. And I think, you know, we have many steps to get there from the observational point of view.
Yes.
Wouldn't it be easier to sell a project if multiple funding agencies are interested in it, because each of them will have to pitch in less money? I would think it should be the opposite. You know, if there is interest from different agencies, it should be easier to get it going, no?
I think one would think that, but I think political reality shows, and Peter, for example, can probably address this very well, that it's very hard to get these interagency projects started. Agencies like to claim the lead of something, and so they don't like to be the second partner in something. It costs them something. I mean, Peter, I don't know if you want to come.
I think what you have to do is you need to, with regard to multi-agency interactions, one, there has to be something of honest-to-God value that each brings aside from money. And that's an important given, I would say. And secondly, you just got to be opportunistic and create the opportunities. They're not going to hand it to you. You have to figure out ways to interact with the appropriate people in the agencies, and it doesn't happen overnight.
Yes, okay. John. Sorry, break after that. And then we go for Fabio.
As a minor codicil to this thing, it's where you're unlikely to get a major missions type science with multiple agencies behind it if you haven't got a rather widespread community behind it. Having sat through the astronomy decadal survey, I was impressed at how this kind of cosmic accelerator astrophysics was not of much interest. It doesn't really appeal to most of the American astronomical community. So sure enough that survey said very little about the subject. Now the physics community has pieces of it which has a different take on this kind of thing, but the same issues arise. The physics community that wanted to sponsor this, get the agencies behind it, has to have widespread support. So there's many meanings to the word be opportunistic. One is to, if you can do something on a smaller scale, then you need to generate, you don't need to generate such a massive, you don't have such a massive political problem. But for major missions, like, Angela, you left aside the question of how you're going to go beyond the 1 order of magnitude count rate in GEM-USO. How would you get to your factor of 10 to the 4? And I rather suspect that's a relatively major commitment. And you sat on the same panel I did. You could see just how far ultra-high-energy cosmic rays went in that community.
Yeah, the good news is they're young people in the field. And I wanted, you want to wrap it up. So I want to wrap up in a little upbeat tone because, I thought there was gloom and doom here, and I'm pretty excited. This year we saw Fermi and Agile finding the pi naught, signature of W44 and IC443, which I thought was going to come up somewhere, and I should have mentioned it. We saw AMS confirming the Pamela positrons and, keeping us, really hoping to see the rest of the data soon. And finally, the ice cube stuff, right? So I think neutrinos is the one thing. So I think it will be much easier to convince the next decadal survey when we have all kinds of results which are now coming up, right? I mean, promising what's going to happen is very different than when you actually have things in your bag. And I think the neutrinos are definitely going to be a major new start in the field in trying to really get, across the damn magnetic fields that these guys love so much, and see directly what's going on too. I mean, it doesn't explain everything, and for the neutrinos to be involved, you need to have the hadrons involved, so it's really at the highest energy. So I think it's really an exciting time, and this will turn around for the next decadal survey to be a little more fun.
Okay, this is a perfect way to stop this conversation, I think. And anyway, I've been told that I have to wrap it up at 12:30 because the ravioli are waiting outside. So let's thank everybody again.